Okay, so we're going to look now at a system of differential equations, and it's really pretty easy to solve the system once you do a few of them. They're not particularly difficult. Let me change the aim of this camera just a little bit. Okay, so what we're going to do is, remember, if you have a higher order equation, you assume that the solution is a multiple of e to the RT. Okay. In this case, we're going to assume a solution, but it's going to be e to the lambda t, because lambda is going to turn out to be eigenvalues of a characteristic equation that comes just from these coefficients. Okay, so we're going to assume a solution x, y equals some constant times e to the lambda t. Okay? Now, in this case, xy is a vector, and your constant is also going to be a vector because, of course, you've got to get two rows in this matrix. Okay? So your text uses K1 and K2. Other text, and I just said K2, so I wrote K2, but obviously this is K1. And K2 here. So it's some column vector times e to the lambda t, just analogous to, again, if you have a higher order equation, you assume a multiple of e to the RT. Just some constant times e to the RT. In this case, your constant has to be a constant vector. Okay, well, then, and this is very straightforward if you write it out a couple of times. Okay, xy prime equals the left-hand side here. That equals the column vector dx dt dy dt. Now that's a theorem that has to be proven, but it's very easy to prove. Just use your limit definition. And since we're only doing a quick survey of systems of equations, we're not going to get all rigorous about it. Okay, we're just kind of doing this as an addendum at the end of the course, which by the syllabus doesn't even officially include this stuff. I think it's important that you see a little bit of it, so we're going to do a little bit of it. Okay, so we have this, and of course then since K1 and K2 are constant, then you just have the K1, K2 times e to the lambda t, and times lambda e to the lambda t, because you're taking the derivative, obviously. So, I don't have that much brain fog today, but I'm still careless. So keep an eye on me. Okay, so we have a lambda out in front of this thing. Okay, well, the right-hand side, and I think I can write this. I think I've got room. X plus 2y, 4x plus 3y equals the matrix 1, 2, 4, 3 multiplied by our friendly column vector xy. This. Okay. Now, our equation then says, well, we can rewrite the equation as dx dt dy dt equals 1, 2, 4, 3 multiplied by xy So, using our assumption, we have lambda times k1, k2 e to the lambda t equals this matrix 1, 2, 4, 3 times k1, k2 e to the lambda t. E to the lambda t divides out, and I'm tempted to shortcut this a little bit, but I'm not going to do it the first time. Even though I think I could actually do that without messing it up, but especially since I know where it's going to go. Okay. So I multiply the lambda here, divide the e to the lambda t both sides, just like we would do if we had an e to the rt moving toward the characteristic equation of a higher order equation. Okay, so everything we've done here, except, you know, we put things in matrix form, mimics what we do with higher order equations, getting the characteristic equation, getting the value of the coefficient of t in the e to the whatever t, rt for characteristic, for a higher order equation, lambda t for a system. Okay, now why do we use lambda? Well, we put this together with this, and I guess I'll write out the intermediate step just because I have room. And I think you maybe are starting to see, if you haven't already, where this is going to go. If you haven't seen it, well, you're going to see it very quickly. So we have this, okay? And I guess I will skip one step because of the way I chose to write this out. Probably should have left the lambda out in front here, but the lambda can factor out, and then we have a multiple of k1, k2, and another multiple of k1, k2, and this gives us 1 minus lambda, 2, 4, 3 minus lambda, times k1, k2, column vector equals 0. Okay, well, it equals a 0 vector, so I should either put an arrow over the 0 or write it out, and I'm going to choose to write it out. Okay, well, this is a homogeneous equation. You have a matrix times k1, k2, it's supposed to equal 0. Now, it's been a while since you had linear algebra, but you understand that unless the determinant of this matrix is 0, you don't have a solution for k1. The only solution you get for k1, k2 is the trivial solution where k1 and k2 are 0. Now I'm going to kind of write that out because it's been a couple of years since you had the linear algebra, even though you did quite well. If the determinant, and I'll write out dt instead of using the absolute value signs. If this determinant isn't equal to 0, then this matrix is invertible, and matrix multiplication is sort of non-commutative. Is not the way to write it out. I know where I want to go, so I was kind of never mind, I was writing it correctly. So K1, K2 is going to equal the inverse of this matrix times 0, 0, which equals, well, any matrix times the 0 vector is going to give you the 0 vector. So K1 equals K2 equals 0, which is worthless. Might be a little hard to read that sentence there. But that's it. So where are we? Where does this leave us? This leaves us with let's see if I can get this all offset here a little bit. This leaves us with we can find a non-trivial K1, K2 only if the determinant of our matrix is 0. Okay, so there we have the condition. And now you see, I think, where the characteristic equation is going to come from. Thus, well, the determinant is 1 minus lambda times 3 minus lambda minus 2 times 4, and it's 8 of course, but it should be 2 times 4, equals 0. So you get what? Negative lambda squared minus 4 lambda. And then you're going to get plus 3 minus 8, so that's minus 5, equals 0. And your solutions, okay, these are all negative. We can still factor this, and, well, let me be real detailed here. Instead of just changing those minuses to pluses, write it out. So lambda plus 1 times lambda plus 4 equals 0. So lambda equals 1 or negative 1, or lambda equals negative 4. Okay, so our solution, or our assumption over here was well, actually, I'm a step ahead here. Well, let's write it out. So xy is k1, k2, e to the negative 4t, or xy equals k1, k2 times e to the negative t. Well, now we kind of have to look back and see that, okay, we have this equation, maybe I can get that on the board here. So, how do we find K1 and K2? We know that if lambda equals negative 4, make sure we're still on the screen. if lambda equals -4, and let me switch over here where I can actually see what's going on. Okay, if lambda equals -4, then this times K1, K2 equals 0, 0, meaning that 1 minus -4, 2, 4, 3 minus -4 times K1, K2 equals 0, 0. So that 5, 2, 4, 7 times K1, K2 has to equal 0, 0. And it's very straightforward. Something's wrong with this. Well, I swear I'm not subject to brain fog today, but my clerical ability doesn't seem to be improved. Let's see where we are. This would give us 5K1 plus 2K2 equals 0. And also 4K1 plus 7K2 equals 0. And these two equations are not compatible. And they, of course, need to be to solve the eigenvalue problem. So I'm probably going to have to backtrack a little bit and repair this solution. And here you're going to get K1 equals, let's solve for K2. K2 equals -5 halves K1. But down here you would get K2 equals -4 sevenths. K1. Now these are not the same. They don't lead you to the same eigenvector. So we've got a problem here. This process is as I've shown it, but I've got to have an arithmetic error or something in there because it's not going to work out. So we're going to stop the video for a second and figure this out.